Hello everyone. It's my great pleasure to present our work. My name is Cheryl. I'm a first-year PhD student at the Chinese University of Hong Kong. Prompt and accurate detection of anomalies is essential to ensure the reliability of software systems. Unlike manual efforts that exploit all available runtime information, existing approaches in automatic anomaly detection usually leverage only a single type of monitoring data. So we studied the usefulness and necessity for using heterogeneous data to conduct effective anomaly detection. In this presentation, I will introduce our work on cross-modal anomaly detection using deep learning. Our work is conducted with the collaboration of CNC University and the industrial cooperator Huawei Cloud. The presentation contains 4 parts, and let's start from the introduction part. Recent years have witnessed the scale and complexity of software systems expand dramatically. However, anomalies are inevitable in large-scale software systems, resulting in considerable revenue and reputation loss. Automated anomaly detection is a primary step in guaranteeing the reliability of software systems. And in practice, many types of monitoring data, particularly metrics and logs, play an essential role in software reliability. However, existing automated efforts usually focus on a single source of monitoring data, which is often insufficiently informative. And intuitively combining different sources can allow better utilization of runtime information. Let me first introduce the data used in this study. Well, logs are semi-structured text messages composed of constant strings which are written by the developers in the code and auto-generated variable values which are determined by the system. And parsing a log message is to remove all variables to obtain a structured log event. And data collected in the same period are regarded as a data chunk. So our aim is to identify whether a chunk is normal or not based on the manifestations of log events and the metrics. Our motivation is based on a study where we find that logs sometimes cannot record fine-grained information. We can see that only less than 4% of positively labeled chunks are anomalous from the log's perspective. Because logging is a human activity, and which is heavily relying on developers' knowledge, well, it's relatively easy to write logs describing severe failures, while subtle performance issues such like the great failures are often hard to identify. So logs capturing such anomalies could be missing. Moreover, we also find that metrics are responsive to system status changes, but still insufficient in many cases. Moreover, their oversensitivity may cause false alarms on uncommon yet acceptable fluctuations. This figure displays an example that a so-called outlier appears even in the fault-free period, where we inject fault during this period. Because such sporadic and transient fluctuations acceptable without affecting the service, thereby engineers may not desire such alarms. And we also summarize the representative faults and their effects on logs and the metrics in this table. And we can see faults can affect the logs and metrics at the same time, indicating their collaborative relationship. We also find that the complementary relationship that a fault can affect one source while the other source keeps unchanged. And basically, logs record the software's internal execution logic, while metrics provide an external view by measuring performances and resource usage. So combining the two can better depict the system status. And we also identify 3 challenges of using different data sources for anomaly detection in general cloud computing systems. Firstly, logs reflect system anomalies mainly through their semantics, like they have some keywords and the sequential dependencies across events. And the metrics record the system status from different aspects. For example, CPU user usage and CPU system usage both characterize CPU usage. And metrics belonging to different aspects may behave very differently, like CPU message are generally stable, but IO metrics can fluctuate dramatically. So their behaviors are complex and diverse, so we need to carefully model different modalities. And secondly, the gap between modalities cannot be ignored, like logs and metrics are in different forms. Logs are textual, while metrics are usually time series. And the same anomaly can affect logs and metrics to very different degrees, like killing the data node during LDA application causes 29 abnormal metric segments, while only one log sequence reports anomalies. So the gap cannot be ignored, and thirdly, there is a trade-off between cost and accuracy. Supervised approaches are effective, but require high-quality labels, which is difficult, costly, and time-consuming. Well, unsupervised learning avoids labeling, but it suffers in accuracies with less human oversight. And we solved the challenges one by one. We first carefully model each modality, specifically according to their characteristics. And we designed a novel cross-modal attention mechanism to align logs and metrics by retaining meaningful information. Also, we present a two-phase semi-supervised training strategy to guarantee accuracy while reducing cost. And I will introduce our methodology. The figure presents the overview of our method, a heterogeneous anomaly detector for software systems via cross-modal attentive learning. It consists of 4 components. We will start from the log modeling, which contains 3 steps: log parsing, log vectorization, and the log representation learning, where we use a parser named Chen to parse logs and use a word-to-vector technique, fast attacks, to embed log events with respect to textual semantics. Then the log event sequences are fed into 2-layer transformer encoders to obtain context-aware log representation. And we design an aspect-aware metric modeling model to deal with the challenge of metrics' diverse behaviors, where we group metrics corresponding to the same aspect into several multivariate time series, which are fed into the inter-aspect encoder, composed of causal convolution layers. The resulting outputs are pulled and inputted into the inter-aspect encoder, also composed of convolution layers, to obtain the representation containing both inter and intra-aspect relations. And we also design a novel cross-modal attention mechanism to fuse heterogeneous representations and bridge the gap between logs and metrics. This model contains 2 attention layers, where the metric representation RM and the log representation RL take turns acting as query and the other one as key and value. The resulting 2 representations are concatenated as the global representation family, and which is then inputted into stacked fully connected layers to obtain the final binary result, normal or not. And we also present a 2-phase semi-supervised training strategy to reduce labor-intensive annotation, where we train the model with a small amount of labeled data and apply pseudo-labeling on the unlabeled data. And we update the model using both labeled and high-confidence pseudo-labeled data until convergence. And this is a visual interface to show the detailed information. And finally, we evaluate our method. We compare Hades with 10 baselines in different training manners based on our collected data set to A and to extra data sets from 2 cloud services in Huawei, which named B and C. And Hades outperforms competitors by a significant margin. And the ablation study also demonstrates the significance of heterogeneous data and contributions of our specific designs for intra and inter-model representation learning. And note that our semi-supervised Hades achieves comparative results compared to its supervised version, which is trained only by the manually labeled data. And we also find that Hades is not sensitive to a predetermined hyperparameter denoted by T, the chunk length, which further confirms its robustness, and this makes Hades easy to deploy and launch in practice. And that's all about our work. Thank you very much.
Thank you, speaker. So we have time for a question. You can use the mic over there.
so much. Just wondering whether there's any deployment already with this methodology in any practical environment. Is there any open source tools we can use to see whether, if we try in different production environment, whether that's going to work or not?
Yeah, thank you for your question. We have already made our code publicly available, and also our collected data, the dataset A, which is from a Spark distributed cluster, and the data and the code has already been released, but it has not been deployed in practice because the time is limited, and I think it will be deployed in Huawei very soon because it's also our collaborated project. This work is also for our collaborated project, so it will be deployed.
Very nice work. So I had a question about the kinds of failures and anomalies that you can detect with Hades. So have you thought about whether you can detect rare events, things that occur, say, with very low probability that you might not have seen during training, and when you deploy Hades, are you able to detect those?
Yeah, it can detect unseen failures because in our paper where you can see the details, we inject very different kinds of failures, but in the training data, only some of the failures can be seen in the training data. So, which means other failures are unseen, and it can still successfully detect those unseen failures.
So is there like a baseline probability by which that event should occur in the training data before you can detect it, or it doesn't matter?
Actually, no matter what kinds of failures, even though there are very different failures, but they will cause similar anomalies from the level of data patterns, like there will be spikes and jitters and some abnormal data patterns. So we focus on the data patterns. So no matter what the failures we can see in the training site, if it can cause some general abnormal data patterns, we can still detect them in the test phase. Yeah.
Thank you.
Thank you very much.
Hello, thank you for the great talk, and I have two questions. So the first one is that how do you generate the pseudo data for training? And the second is that how many types of anomalies that require both logs and metric to detect, or all of the anomalies can be detected by using only one type of data? Thank you.
I will show you this figure. Since firstly, there are a few label data where the label data will train the model in a supervised way. And so the model has already been trained for several epochs. And after that, we use unlabeled data, and we use the trained model to predict the unlabeled data. And we can easily to get the confidence score because there will be probabilities naturally because it's a neural network. And so with high confidence, like more than 80%, we can regard the labels are pseudo labels. And if the confidence scores are too low, we just ignore those labels. And those pseudo label data can be then blended with the label data, which are labeled by human beings. And together, they will train the model. I'm sorry, could you repeat your second question?
Okay, so how many types of anomalies that requires both logs and metric to detect, or all of the anomalies can be detected by only one type of data?
I have another ablation study that you can see if we just use logs and both the FS score recall precision and all the evaluation measurements will be reduced. And so it means that if you only use one kind of data source, there will be many anomalies cannot be detected. But actually, the exact numbers can be different among different data sets.
Okay,
Thank you.
Okay, perfect. Thank you very much. Let's thank the speaker again. And we move to our second talk from Chetan Bansal from Microsoft Research. We will talk on a method for recommending root cause and mitigation steps for cloud incident.
Hi everyone, I'm Chetan Bansal. I'm a researcher and research manager at Microsoft. Today I'm going to present our work on recommending large root cause and mitigation steps for cloud incidents using large language models. This is joint work with our summer intern from last year, Toufique, Ahmed, and my colleagues at Microsoft. So today, in today's talk, I'm going to talk about briefly about the motivation behind this work, like why we looked at this problem and the approach we took. And also, I'm going to talk briefly about the emergence of large language models and why they are interesting for the software engineering domain. And then I'm going to talk about how we are leveraging GPT OpenAI model for incident diagnosis, followed by the effectiveness, some experimental results on the effectiveness of these LLMs, large language models, and also how the model performs in a fine-tuned setting versus zero-shot setting. And then I'll wrap up with summary and some brief thoughts on the future work. So before going into the details of this work, I'm going to briefly talk about the incident management domain itself. Like as we have moved from boxed software to service-oriented architecture, monitoring these services have become very important, like especially when these services undergo unplanned expected behavior. Then it's really important to understand and root cause and mitigate what the anomalous behavior which is demonstrated by these services. And as you can see here, all major cloud platforms regularly go through outages and incidents because of various reasons, such as configuration issues, dependency issues, infrastructure failure, and so on. So it's really important to have like a well-defined, well-oiled machinery for incident management, incident root cause, incident diagnosis, and mitigation. So, as I said, like incident resolution is a very important process for all of the cloud providers because these services are being used by a lot of like real-world users across the world, all the way from like health services to airlines and so on. So they're actually real things dependent on these services being operational, apart from like entertainment like Netflix. They're actually like life-critical processes and people who are dependent on these services. So talking a bit about incident resolution itself, so it's generally a non-trivial process because it requires significant amount of domain knowledge and effort when an incident happens. So it's really important to minimize the impact of these incidents on the end users and also on the developers who are looking at the incident so that we can improve their productivity while reducing user dissatisfaction and financial impact. So the goal of this work is how we can reduce on-call effort and customer impact by automating incident diagnosis processes with recommendations from large language models. And here at the bottom, you can see the incident lifecycle where it goes all the way from alerting, engagement and triaging to investigation and resolution. And here, like this, there have been several works which are focused on the detection part, the triaging part. So here in this work, we focus on the investigation part, like how we can accelerate the root cause and mitigation. So briefly talking about large language models, like I'm sure like everyone in the room is familiar with ChatGPT and this emergence, but I'll still briefly talk about why it's becoming more and more important. So as we know that in the last 4 years, the model sizes have grown exponentially, like starting with about 100 million parameters with Elmo model on the left, all the way to 180 billion parameters in GPT-3 and 3.5, and even bigger models which are emerging from OpenAI, Google, Microsoft, and academia. So what that has done is that it has enabled these AI models to be really good at generating contextual recommendations and coherent recommendations for a wide variety of tasks. And they're becoming really good at reasoning over natural language data with self-supervised learning. And what we have also observed is that they have become really good at very important common world tasks such as question and answering, machine translation, code generation, and GitHub Copilot is a great example of that, which is being used in practice by thousands or hundreds of thousands of developers today. So with that in mind, we started looking at how we can leverage large language models in the incident lifecycle to help our on-call engineers and improve our service reliability. So what we did was we started by collecting historical data from the Microsoft Cloud Services for the last 4 years. And the goal is that can we take this historical data and then at the runtime, when an incident happens, then take the available information such as the incident title, incident summary, whatever details are present, and then pass it on to the large language model and generate recommendations, which are then leveraged by the on-call engineer for root causing and mitigation of the incident. And here you can see the sort of the life cycle where first the incident is created on the incident portal, then the incident owner is sort of looped in, and then that information is passed to the GPT LLM model, and which then generate recommendations and provides, which is consumed by the incident owner. So going a bit more into details of the experimental setup. So here we leveraged fine-tuning of the GPT-3 and 3.5 models. Fine-tuning is a process where we adapt the weights which are learned at the pre-training time on a new task or a new data set. So we went for the fine-tuning of the models so that we can adapt it for the incident management domain, because the vanilla off-the-shelf model is not really aware of microservices or service architecture or the details of these services. And here we collected the historical data from about 1,000 plus services and use that for the root causing and the mitigation tasks separately. And here you can see the details of the data sets for training, validation, and testing. So going briefly a bit into the results of the experiments. So the first thing we did was, again, a very low-hanging fruit, which is how effective are these models on the root causing and mitigation task. And the evaluation itself is non-trivial because we have tons of metrics from the NLP domain. But what we have seen in the literature is that these are not always reflective of the actual performance and the usefulness to the end users. So we started with a set of metrics which come across lexical and semantic evaluation. And here you can see the comparison between GPT-3 and 3.5 models. And what we observed was that the GPT 3.5 model, which is sort of state of the art and better than GPT-3, outperformed all the other GPT-3 models on these two tasks. One thing I do want to clarify is that, or draw your attention, is that if you look at Curie, Codex, and DaVinci, which are like models of different sizes, we did not observe any sort of pattern or correlation between the model size and the performance. And and that may or may not reflect on the actual performance on the human evaluation. And then here's some, again, we also did a human evaluation of the LLM, large language model, and we interviewed about 30 on-call engineers and asked them to evaluate the readability and the correctness of the recommendations. And more than 70% of the engineers provided a positive recommendation or evaluation of the recommendations. And here you can see some verbatim quotes, such as even though the recommendation wasn't fully correct, but it still helped them point in the right direction. And in one case, the model actually produced an exact recommendation. But another thing which is obvious and interesting is that, given the limited context which is input to the model, it may not always be possible to do a complete root cause analysis or mitigation, because things like logs or conversations which are happening outside the incident portal are not really processed by the large language model. So that's sort of something we're looking at as future work. So moving on, we also evaluated the performance of the model in a fine-tuning versus zero-shot setting. And as expected, because of the zero-shot setting, the model is not really aware of the incident management domain. So expectedly, fine-tuning gives a significant boost, more than 100% improvement in several of the metrics. So wrapping up the talk, I just want to conclude by saying that we conducted the first study of leveraging state-of-the-art large language models for assistance with incident diagnosis. We conducted a rigorous and large-scale study on over 40,000 incidents from several years across Microsoft, and we evaluated several aspects such as the impact of model size, fine-tuning, incorporating additional context, and multiple steps in the incident lifecycle. We also did offline and human evaluation, which shows the promise of using these large language models for incident management, incident automation, and more specifically on tasks beyond code completion. In terms of future directions, there are several approaches which I think are interesting for the community, and also something we are trying to look at, which is hybrid approaches which combine fine-tuning with in-context learning, developing multimodal large models which can not just understand natural language, but also logs, time series, language, etc. Moving from one-turn recommendation, which is what we're doing now, to also like an interactive modality where it can be a continuous dialogue between the LLM and the incident owner and the incident setup. So with that, I'll just wrap up by briefly plugging in about my research group. So I'm part of the Systems Innovation Research Group at Microsoft. We work at the intersection of software engineering, AI, and systems. We are always looking for summer interns, researchers, academic collaboration, so please do reach out to me if you're interested in collaborating. And thanks for listening to the talk.
Let's thank the speaker. It's time for a question. Oh, there.
Great. Thank you for the interesting talk. So I had a question about the experience from one of the engineers where they said the LLM was incorrect, but it still helped them to find the root cause. And can you say a little bit more about it? Because one of the standard criticisms of LLMs is that they hallucinate and make up situations. So how does that square with this observation?
Yeah, so what we have seen is that the performance of the LLM varies vastly across different incidents, because as you can imagine, it's a very huge space, right? You're talking about like different types of incidents, all the way from machine-generated to human-reported, from infrastructure to code issues to configuration and so on, right? So in this work, we did a breadth-first evaluation where we took all the incidents, about 40,000 incidents. Now what we're doing is we are going depth first. We are trying to find pockets of incidents where the model works better than not. And to your question, so our approach is not to deploy them without human in the loop. So because these LLMs, as you say, hallucinate and can be often wrong, and AI can never be 100% correct on hard tasks. So we'll always have human in the loop, and these are just pure recommendations which the on-call engineer can either accept or choose to ignore.
Thank you.
Thank you so much for the great talk. One question, because this prediction of root causes are based on 40K incidents in the history, right? So how do you evaluate, or did you notice any challenges for this model to understand or predict the root causes for the new incident, which could be very completely different from historical incident?
Thank you. That's a great question. So one thing we did, which is also a best practice, which is we divided a data set on a temporal basis. So the training set is actually the beginning, is I think 60% or 70% of the instance, and then we have validation, and then we have test. So I think that aspect is already evaluated in this offline and the human evaluation. But to your point about the liveliness of the data and the model, so I think that's a challenge which is there in the fine-tuning process itself. So what we are going to do, we are actually working on right now, is combining fine-tuning with in-context learning, where we have a fine-tuned model which is aware of this domain, but then we incorporate new examples which are more recent, and then the model is able to take best of both the worlds.
Thank you.
Okay, thank you for your great talk. And I have one question about your input is an incident summary of an incident. But if you already have the summary of the incident, it means that you have understanding about this incident. So you have the understanding, maybe you can already have some root cause or the mitigation steps, you already have that. So how do you use that? Do we need to first draft a summary about an incident first, then we input the summary into this LLM? Do we have to do this?
Yeah, that's a great question. So just a clarification, that summary is probably a misleading word which we use at Microsoft in that incident tool. It's more of a description which is provided by the person or the bot which is creating the incident. So it's not really a summary as such. It's more of a description which is provided at the time of incident filing, incident creation. So it's not an actual summary. It was a misleading term.
Okay, thank you.
I have time for a very quick question. Can you estimate the effort for filtering through your data set for preparation? There was a slide with the blue boxes.
Right. So maybe I can go back there quickly. So in terms of effort, so I think you mean like computational effort? So yeah, so we do have, thankfully, now big data systems at Microsoft where all of this instant summary information and postmortems and all are stored. So the effort is not really that much because we do have a lot of computational power. So it's like I can give you a number, like we can export this data in order of like a couple of days. But the devil is in the detail. Like it depends on what underlying system you're using. So, but to answer your question, it took us a few days to generate the data set. And also now we have several different researchers working on this problem. So we also have shared data sets.
Thank you. Let's thank the speaker again. And we move to the next talk. Perfect. Time. We have Cheryl Lee again from the Chinese University of Hong Kong, and she will present the work on troubleshooting framework for microservices.
Good day, everyone. My name is Cheryl Lee, and I'm excited to present my paper on microservice system reliability challenges and our proposed solution. I'm a PhD student at the Chinese University of Hong Kong. This paper was also co-authored with a researcher from CSE University, and together we adjust the limitations of existing approaches to automated troubleshooting in microservices by integrating anomaly detection and root cause localization based on multi-source data. I will present the 4 parts one by one. And microservice systems are increasingly appealing to cloud-native enterprise applications for several reasons, including resource flexibility, loosely coupled architecture, and lightweight deployment. However, anomalies are inevitable in microservices due to their complexity and dynamism. Even worse, an anomaly in one microservice could propagate to others and magnify its impact, resulting in severe failures and huge losses. This shows an example where a failure in one microservice called order may delay all microservices on the invocation chain. We can see the latency time is especially high in general order latency time. And so we need anomaly detection to identify the existence of an anomaly. And it's not enough. We need finer ground information besides the anomaly existence. That's where root cause localization comes, which answers the probability of each microservice being the culprit. And besides logs and metrics that are widely used in general software systems, microservices usually employ traces to record the process of microservices responding to a user request, as different microservice instances conduct a series of small actions to respond to the request. For example, the request to create an order may contain many downstream steps. Like we can see, if the user requests create an order, the order, cart, and payment, a lot of microservices will also respond to the order in a flow. And the process, a microservice caller can invoke another microservice callee to conduct the following action, and the callee will return the result to the caller. We name this process as invocation. Like the order asks the microservice cart to empty the shopping cart after ordering the good in the example. So the time consumed by the whole invocation is called latency, including the request processing time inside the microservice and the time spent on communicating between the caller and the callee. So in the real world, there can be thousands of microservices, and tens of them can be involved when responding to a single user request. So it's extremely challenging to achieve automated root cause localization with such complex dependencies. Our work is motivated by finding that inaccurate anomaly detection results can lead to poor accuracy in root cause localization. Specifically, existing localization approaches perform a pipeline method where the method conducts anomaly detection first, and if an anomaly is alarmed, then the localizer is triggered. The detector and the localizer are trained and work separately. Unfortunately, incorrect anomaly detection results can perform a negative impact on the following localization by introducing noisy labels. Even worse, as we summarize 3 main kinds of anomaly detection approaches used in the root cause localization papers, we find that current localization-oriented detectors are usually model-based, and they deliver unsatisfactory accuracy and introduce noisy data. So if we simply combine SOTA anomaly detectors, which are mostly learning-based, with the localizers, that will reduce efficiency and incur duplicated learning process, in which we first learn detection-oriented representations from the inputs and learn localization-oriented representations from the same inputs. So such a pipeline ignores the close relationship between the 2 tasks and the shared knowledge. So in summary, the previous approaches always apply the same pipeline pipeline, which suffers a key limitation by separating the detection and the localization tasks, making the localization troublesome. Moreover, previous root cause localization approaches usually rely on traces only. Certain latency or error rate in traces can suggest a microservices availability, yet fine-grained information like memory usage reflecting the intra-service status is still unknowable. And it's natural to think about logs and metrics. So this results in our methodology. The key idea of our method, which is named Eadro, is to force a model to learn fundamental representations, revealing anomalies via multitask learning. That is, a norm detector and root cause localizer are trying jointly. We learn the intra-service behaviors based on multimodal data and capture dependencies between microservices to infer a comprehensive picture of the system status. This figure displays the overview of Eadro containing 3 phases. Let's introduce the first phase. As we mentioned, that we consider logs and metrics besides traces, and this phase aims to model the different data sources individually. Log modeling is conducted in a 3-step fashion, where considering the complexity of microservices, we desire lightweight techniques, and we find that log events in benchmarking microservices are usually very short, which means their semantics can be limited. So we model the occurrences of log events instead of log semantics. Specifically, we first parse logs into events and use Hawkes process to fit log events occurrences by estimating the parameter intensity. This is because we observe that the pass event increases the likelihood of the event's occurrence in the near future, fitting the assumption of self-exciting process. And the estimated intensity parameters mu are composed of intensity vector, which is fed into a fully connected layer, and we obtain the log representation. And as for metric modeling, we use a one-dimensional dilated causal convolution layer and a self-attention layer to learn the temporal dependencies and cross-series relations of metrics. And the metric representation shares the same dimension of the log representation. And inspired by previous works, we extract latency from traces and transform it into a fixed-length univariate time series by calculating the average latency at each time slot for each callee. Similarly, the latency time series is fed into a convolution layer followed by a self-attention operation to learn the latent representation. At the same time, we can extract a dependency graph based on the historical evocations, which will be introduced in this phase, where we aim to learn microservices over status and draw a comprehensive picture of the system. By regarding microservices as nodes and invocations as edges, we can extract a dependency graph from historical traces. Afterward, we fuse the 3 modalities representations of each microservice by concatenating them and feeding them into a gated linear unit. We then apply graph attention network to learn the dependencies where the fused representation of each microservice serves as the node feature. Eventually, we perform global attention pooling on all nodes and to obtain the final representation. Lastly, either integrate a norm detection and root cause localization with joint learning, which can help the model focus on anomaly indicating features, as the other task detection besides localization provides additional evidences for the anomaly relevance for feature extraction. In particular, the previously obtained representation is inputted into the detector, and if an anomaly exists, the localizer trigger to rank the microservices according to their probabilities of being the culprit based on the same status representation. The detector and the localizer are both composed of fully connected layers. They are jointly trained and by sharing a training objective, which is a weighted sum of the 2 sub-objectives for the 2 tasks respectively. So we can fully leverage the shared knowledge and integrate to closely related tasks into an end-to-end model. So this is also a visualized demo for our Eadro, which the engineers can see the root cause list. And finally, we evaluate the effectiveness of Eadro in anomaly detection, root cause localization, and we also investigate the contribution of each data source. Well, experimental results on two widely used benchmarking microservices demonstrate the effectiveness of Eadro, which surpasses all compared anomaly detectors by more than 50% to more than 90% in FY score. And also it achieves SOTA localization results with 290% to more than 5,000% higher in top 1 hit rate than 5 advanced baselines. And it also outperforms our derived methods by a significant margin. And our ablation study highlights the contributions of each involved data source, and we find that traces contribute the most to the overall effectiveness. And this is all about our work. Thank you for your listening.
So we have time for questions.
Thank you so much for the great talk. One question about the dependency graph learning from the tracing and logging data. Just wondering, do you have any evaluation regarding that accuracy? And is there any source code that we can try to, apply to different data sets? Thank you.
And data used in this study are from two benchmarking microservices, where we first built the microservices based on Docker and perform some tasks and collect the data. We also deploy a lot of monitoring tools to collect the logs, metrics, and the specific details are also introduced in the full paper. So all the data and the code has already been released, so you can access them. Yeah, thank you.
There's one more question.
Hi, thanks for your talk. One question I'm curious about, because your method is a supervised method, I think the training data has a big impact on the, the approach will have an impact on the training data. So how do you construct your training data and the testing data set in your evaluation?
Well, we just split the data set according to the time they collected. Like the first 16% of the data are split as the training one, and the later 10% are as the validation site, and the last 30% are as the test data.
So is it split by randomly or?
According to the collecting time. Just split it.
Okay. Yeah. Okay. Thank you.
Thank you.
We have time for more questions. Meanwhile, I will ask a question. So, your approach seems focused on anomaly detection approaches that are focused on localization, but is this a mandatory requirement, or it can also deal with more sophisticated approaches that for anomaly detection that are not really focused on localization?
Sorry, you mean this? Is there any other approaches for root cause localization, or can I address more questions, more tasks?
Yeah, that's it.
Actually, even though this tool is based on microservices, where we can only localize the root cause in microservices, but there are a lot of different software systems that will have such dependencies. Like in a traditional distributed system, sometimes we may want to know which machine, physics machine is the root cause, which one is abnormal. And in serverless systems, we may desire to find whether the function works well. So there are also different systems have such dependencies. And even though this tool is just for microservices, we can also extend this based on modeling the dependencies and to address more problems in different systems. Yeah.
There's a question over there. That's one.
Yeah.
Thank you for the presentation. I was wondering, because this is a framework for microservices, so which means there were a lot of services shared by different products. So I want to know, the anomaly detection is based on product level or on service level. For example, you had an example about e-commerce services. I think it's in page 11 or something. And you mentioned that it's kind of like when user complete an order, then it will trigger the other service, and then you could use that as kind of log system to detect anomaly behaviors. And if there are like several products share the same services, how do your like framework or like your algorithm to send out the anomaly?
The anomalies are at the OS level. Like we may inject a CPU hog to occupy the CPU and to make it to make the CPU metric extremely high. Actually, if the faults can be reflected in the different data sources, then the anomalies can be detected. But if there are logic bugs, and on the other hand, if there are salient failures, like even though the data source cannot reflect the faults, but there is still some bugs and can be detected by the software engineers instead of data-driven tools, then those anomalies cannot be detected. So since it's data-driven, so the limitation is based on the data. Thank you.
Let's thank the speaker again. We move to our fourth talk by Guamba Yu from Yat-sen University, and he will talk about a way to reduce log hotspots.
Hey, hello everyone. I'm Guamba Yu from Yat-sen University. It is my honor to be here. Today I will introduce log reducer. Logs records the running information of a system. It is a popular data source used by SREs to check system status, detect anomalies, and diagnose root cause. However, logging is a double-edged sword. It will incur high storage costs. For example, in WeChat, it generates about 20 PB logs per day. We need to spend more than $10 million to store it per year. Therefore, we would like to reduce the massive log amount to decrease the operation cost. After investigating the distribution of logs, we find that most of the log overhead is due to a very small number of log templates. The log template is usually considered as the static part in logs. We take the smaller number of log templates that occupy a lot of disk space as the log hotspots. Consequently, we can find that reducing log hotspots is cost-effective approach for decreasing the log amount. This is the motivation of our work. To gain a deep understanding of the impact of log hotspots, we conduct an empirical study in WeChat. We choose the top 20 services with the highest log storage in WeChat. We found 57 log hotspots from the 20 services. Based on the hotspots, our study aims to address the following research question. For research question 1, we found that only one service do not contain any log hotspots. Furthermore, we found that one hotspot even occupies 95% of the storage of that service. This is also shows that reducing log hotspot is a cost-effective approach. We only need to handle one log statement, but we can reduce 95% of the storage. For question 2, we monitor a service with hotspots before and after fixing these hotspots. The new version only modifies the log statement compared to the old version. From the figure, we can find that the version with hotspots consumes up to 5% more CPU and suffer up to 3% more response latency. For Arc5, we use the fixing time to denote the time it takes for developers to fix log hotspots. It includes the time taken to modify program, test program, and release the new versions. From the figure, we observe that most of the log hotspots cannot be fixed in time. For 97% of log hotspots, it takes at least 3 days to fix them. As shown the above study, log hotspots are common in different services. In this study, we propose a log reducer, which is a non-intrusive and language-independent framework designed to filter log hotspots. The figure shows the framework of log reducer. We divide the reduction products into offline and online process. First, we introduce the offline process. Before alerting developers, we need to parse log logs. We combine the log signature matching and frequency analysis to parse a log. We use the co-localization of log statements as the log signature in this paper. Giving a low log message, log parser first extract the log label, service name, and the log signature from log headers, and filter out numbers in log content. After that, log messages are clustered into groups based on their log signature. For each group, log parser builds a frequency table of words like the picture. And log parser looks for words with the same count as the log number. We extract log templates based on a key property. If words appear in every log in a cluster, then it is a static work. Finally, log parser considers all static words as the log template. Log parser also records the total storage of each log templates. And then the hotspot classifier model takes the log template and corresponding storage information as input. It identifies log hotspots from all log templates based on the equation. If hotspots exist, hotspots classifier will trigger the reduction process in the offline and online process. And then we will alert developers with the information of log hotspots. We provide a dashboard like the picture to guide developers to reduce log hotspots. Finally, developers reduce the log hotspot and release the new version. We apply the log reducer offline process in WeChat in 2022, the log storage in WeChat dropped from about 20 PB to 12 PB per day. However, the offline process has some limitation. The first limitation is that fixing hotspots takes a long time. Let's recall the question 5. Developers need an average of 9 days to fix hotspots. Furthermore, we find that new log hotspots appear frequently after the old log hotspots have been fixed. Therefore, reducing log hotspots is not a one-time task, but a repeated one. So, in offline process, services are affected by log hotspots until the new version is released. It is intuitive for us to wonder that can we avoid service being affected by log hotspots before fixing them? The first idea we have is to filter logs in the log collector. Filtering hotspots in log collector can reduce storage costs successfully. However, it cannot reduce the printing overhead and network transmission overhead. Therefore, this is not the solution we want. The second idea is to filter log hotspots in log agent. We use the regular expression to filter hotspots like the picture. Filtering hotspots in log agent can reduce storage costs and network transmission overhead successfully. However, it cannot reduce printing overhead. Therefore, it is not the solution we want to. The third idea is to filter hotspots in the Linux kernel. In this approach, we can reduce the storage cost, the network transmission overhead, and printing overhead. In addition, filtering in the Linux kernel is more efficient than filtering in the user space. Therefore, we believe that it is ideal approach filtering log hotspots. Next, let me introduce the online log filter, which filters hotspots in Linux kernel with extended Berkeley package filter. It means the eBPF. the online log filter is triggered by hotspot classifier. Then the Python log filter loads the eBPF code and log signature of hotspots into kernel space. After that, eBPF log filter intercepts the sys code, matches the log signature, and drop log hotspots in the kernel. We have implemented the online log filter based on the Python and BCC. The figure shows the overhead for log filter when filtering hotspots in kernel under the different log volumes. From the feature, we can observe that it increased latency by about 500 nanoseconds for each request when filtering 100,000 logs per second. Okay, let me conclude the presentation. Reducing log hotspots is a cost-effective approach. We conduct a systematic study about the log hotspots in real-world systems. We apply log reducer offline process in WeChat. The storage in WeChat dropped from about 20 PB to 12 PB per day. We propose a non-intrusive and language-independent log reduction framework to identify log hotspots automatically and reduce them on the fly. Okay, that's all my presentation. Thank you for your attention. More details can be shown in our paper. I'm waiting for questions now.
Let's thank the speaker. We have time for questions. Please.
Thank you very much for the great presentation. One question. I understand this log reducer worked pretty well for WeChat. Just wondering if we have a different application, could this also work as good as it is for WeChat? And how much customization we need to do in terms of changing the code?
Okay. For the generator, we have Okay. We have conduct empirical study shows that many the WeChat have more than 20,000 services. We find that most of the service in WeChat contains the log hotspot. I think that maybe in the meta it also has some problem too, because the developer may not focus on the log overhead.
My question is, if we would like to use your tool, how much customization work we need to do, or do you have this open source we can just leverage directly?
I think that you don't need to customize any. We open source the eBPF tools in the GitHub.
Okay, we can pretty much use it directly and then give it a try.
Maybe limited by the Linux kernel, because the eBPF needs a more lastly Linux kernel, like after Linux kernel 5. Okay.
Got you. Okay. Thank you so much.
Thank you.
Okay, we have time for one more question. And I have a question. I would like to better understand your definition of log hotspot, because you focus on the template. Is it a template in which the fixed part is verbose, like in terms of characters, or is it because it contains a lot of dynamic parts, or a lot of parameters, or is it a combination of the two?
Actually, we are not okay in this picture. I think that Maybe I not really understand your question. Can you repeat?
We can, I think we are running out of time. We can take it offline, maybe.
Okay.
Okay, let's take the speaker again.
Thank you.
So we now move to the next talk, which is part of the software engineering practice track. So our next speaker is Zhang, and we're talking about actionable performance anomaly alerting. Please.
Okay, hello everyone. I am Zhang, a master student from South University for Science and Technology. Welcome to TraceR toward actionable performance anomaly alerting for online server system. This is joint work with SASTEC, Microsoft, and Chongqing University. First, let's discuss online server system. Those systems form the backbone of modern internet applications, which are mostly based on Microsoft architecture and are deployed on cloud server. Take Microsoft Exchange Mail as an example, which is designed to deliver email between mailbox. When an email is sent, it passes through various server components until it reaches its destination. The log system will record span during this process, capturing time span and parent trail information. By analyzing this data, a comprehensive trace for email delivery record is created. The Exchange server is made up of hundreds of server components and generates billions of traces per day. To ensure the stable running of this huge system, an efficient anomaly detection system is necessary. Then let's discuss performance and actionable anomaly for the title. In this work, we focus on performance anomaly, which is issue causing a decline in component efficiency, such as increasing response times or decrease the servability. Additionally, we hold our algorithm to detect actionable anomaly, which has two key features. Firstly, they are serious incidents with significant impact on the system, like affecting multiple data centers or lasting for long duration, deserving further analysis. Secondly, they are interpretable, helping support engineers understand the anomaly detect process and diagnose the issue effectively. Next, I will introduce the current mainstream anomaly detection techniques. One of the popular methods is the anomaly detection technique based on distributed trace data. This method will learn the pattern for normal trace from a large data set, which is then used to identify anomalous trace data. However, those techniques may encounter certain challenges, such as high overhead of deep learning model and limited interpretability of those models. The technique called monitoring-based anomaly detector is simple. It applies monitor collecting data from each component, like CPU usage and response time, to find the anomaly with rule-based model or algorithm. However, the monitor only looks at one component at a time, resulting in many false positives and duplicate anomaly. Then we summarize the challenges in detecting anomaly in online server system. Firstly, a large amount of data make it difficult to collect, process, and detect anomaly in time. Secondly, detection accuracy may be limited, lead to issues like false positive and redundant anomaly. In addition, current method lacks interpretability, which is crucial for engineers to diagnose the anomaly. Finally, most methods rely on unsupervised learning, which make it difficult to integrate expert knowledge to identify actionable anomaly. To address those challenges, we first analyze trace data from the Exchange system. The trace data captured over a 1 month duration for the Exchange server, including both actual anomaly and false positive. Through our analysis, we identify the following insight. Firstly, we can calculate a north inclusive and exclusive latency from the trace data. Inclusive latency refers to the total running overhead of the component, while exclusive latency represents the individual overhead of component. As shown in right figure, using the screen is no signal in here.
Can someone of the technician please check the monitor screen? Apparently there is no...
Oh, I can see it now. Okay. And on the right here is an example of non-actionable anomaly, even though the latency data show an anomaly within the component. There is no anomaly present in a more important KPI time series data. This leads the engineer to believe that further action is not necessary. Classifying actionable anomaly requires different knowledge from each project. Therefore, expert knowledge must be included to determine whether the anomaly is worthy for further diagnosis. Here we show the overall architecture of our anomaly detection approach, which contains 3 main parts: trace processing, anomaly evaluation, and alerting and feedback. Then I will present how trace are address various challenges. Firstly, in the trace processing stage, due to the large volume of trace data, we need to make a set to sample it. Then we aggregate the trace data into time series data at different levels of guarantee. Moreover, we implement a simple and effective anomaly evaluation algorithm and anomaly feature extractor to reduce the overhead of detection. Next, for detection accuracy, we identify 2 common anomaly detection approaches. One uses a model for the entire system. The other trains a single detection model for each object. We found that using a unique model for each object simplifies anomaly detection. And we also found that exclusive latency proved to be more reliable metric. Therefore, in anomaly evaluation and alerting stage, we will calculate the anomaly score metric for each subject based on the exclusive latency as the results shown in an anomaly results table. In feedback stage, we employ an interpretable machine learning model to learn actionable anomaly threshold based on engineering feedback. First, we say the results of the anomaly evaluation for each detection subject in the feedback dataset. Next, we select part of the detection subject for the feedback dataset for the engineer to label. Later, the labeled and unlabeled sample in the feedback dataset are fed into simple decision tree model with just 3 sub-decision trees for semi-supervised learning. They help us determine actionable anomaly threshold while maintaining the model interpretability. Eventually, the detected anomaly will be reported to the engineer for further diagnosis. In the evaluation session, we collect 2 datasets. One is a real dataset from the extract mail server, and we label the anomaly with the engineer. Another dataset comes from an open source microservice system, where we introduce anomaly based on anomaly injection follow peer-reviewed work. For the baseline, we choose nice state-of-the-art and heuristic baseline from existing approach. We then evaluate the performance of trace R under 2 datasets and present the pass guarantee level in this table. The evaluation results shown here are without the feedback module. We rely only on anomaly score and a simple threshold. The results indicate that trace R significantly outperform the previous baseline in both datasets. Then we further evaluate the effectiveness of feedback module. With feedback count in the graph showing the total number of samples labeled by the engineer. F1 score representing the performance metric and different line for different feedback strategy. It can be seen that K-mean purpose can achieve relatively good performance in both the early and later stage. It is a 25% improvement compared to the performance without the feedback module. Moreover, we have successfully deployed TraceR to extract mail system. During a 2-month experiment period, TraceR was able to achieve a precision of 0.93, which significantly outperformed the previous approach used by extract mail team. Finally, the TraceR runtime overhead on the whole system was satisfied the engineer's requirement. Here I present the interface of TraceR anomaly detection results. This interface displays essential detail about the anomaly to assist engineers in diagnosing them further. Additionally, you can further check the decision tree structure and the anomaly transfer part in more deep. Finally, to conclude, in this work, we present TraceR, an effective, actionable performance anomaly detection approach. We conduct comprehensive experiment on 2 offline datasets. The results show that TraceR outperformed previous state-of-the-art baseline. And we had deployed TraceR on extract mail server in a real production scenario, and TraceR significantly outperformed previous baseline. That's all my presentation. Thank you.
Let's thank the speaker. We have time for questions.
I'm just curious about how the anomaly features are extracted. Like they are statistical model based. Like you should calculate the mean and the standard deviation, or there are learning based methods for the feature extraction, or they are manually defined.
Yes, thanks for your question. The anomaly feature is installed in the statistical metric, like calculate the mean and the standard deviation of it, and calculate finally the final anomaly score.
So, have you ever used some feature engineering tools, open source feature engineering tools, or you design those statistics features based on your expertise?
Yes, we had discussed those features with the engineer, and to discuss with them to check which feature is most useful in production scenario.
Yeah, thank you very much.
Thank you.
25% increase with feedback from the label data from the engineers, right? Just want to understand roughly how many labels did we collect that can generate 25% improvements of the model?
Oh yes, we can check for this figure. The feedback count is showing in the XS, like, and so if we want to achieve a 25%, it seems to be 100 feedback is okay.
We have time for a few more questions.
Okay, thanks for your talk. I have a question on if we alert for SREs, is only one trace be determining anomaly we will alert the SRE, or there is more than like 100 trace abnormal and we will alert?
Oh yes, thanks for your question. Actually, the detection subject of our model is not in trace guarantee. Is in the server microserver guarantee or the microserver component guarantee. So we will report the location of the component to the engineers, to SRE, and also and they can further check the trace of those components further.
Okay, if in normal time they have some abnormal trace, how do you filter the false negative?
We only need to report the abnormal server component to the SRE, and they can further check it why the component is abnormal.
Okay, thank you.
I have one final question. So in the paper, you said that you focus on trace-based approaches, and you said you did not consider log-based approaches. However, often in software engineering, traces and logs are used interchangeably. Can you please comment on the difference on your assumption and definition of traces versus logs?
Oh yes, in the paper we talk about the loss-based decision anomaly detection techniques, but we think the log data also will be high detection overhead, and it also poor interpretability. So in this work, we mostly use the statistic metric to detect the anomaly.
Perfect. Let's thank the speaker again.
Thank you.
And we can prepare for the next talk. It's a journal first presentation. It's a paper published in ACM Transactional Software Engineering Methodology. And our speaker is Danny Ways from KU 11. And he will talk about an approach for formally modeling self-adaptive systems. think you can start.
Hello all. So I will talk here about the joint work that I did actually with my whole research team for a period of over 10 years, where we engineered here a solution and we validated in many different cases. So let me start with first maybe quickly saying what is self-adaptation, although that the word is here in the title of this section. So far, most of the work I have here is all about one stage in self-adaptation, where you try to detect something that requires the system probably to be adapted. So when we talk about self-adaptation, we talk about a feedback loop system, where that feedback loop monitors the system, for instance, to detect anomalies, but then action needs to be taken to make sure that certain goals are achieved. For instance, this can be a kind of IoT system where you track the interference in the network or the load on the system, and then to maintain that the packet loss stays below a certain threshold and the energy is, the consumption is minimized, then you can adapt, for instance, the network settings. Now, self-adaptation can come in very different ways. It can be applied on the whole system. It can be applied on a part of the system. A human can be in the loop, or a human can be on the loop. All these kind of different variants exist. We recently did a really large study where we interviewed about 184 companies, and what we saw is that these techniques are widely used in practice. Over 50% of the companies actually apply these kind of techniques, and most other companies actually say that they are have the intention to do it in the future. So let me now come to active forms, what this talk is about. Active forms is actually an end-to-end approach to engineer such feedback loops as I showed you before. And it starts in the design phase, where you first design a feedback loop model. For that, you take the traditional input as domain knowledge, the goals you need to achieve, the architecture of the underlying system that you want to adapt. And we also provide a set of templates that help you with designing these feedback loop models. And so you design them, and then you verify them and make sure that you have verified feedback loop models that in fact comply with a set of requirements that you want them to be compliant with. Then you deploy that model all together with a model execution engine that we have developed, and together also with a runtime verifier that allows you to verify that model at runtime. And that deployed model is then executed, started, and then from then on, that model is taking action, monitoring the system. If adaptation is required, based on the adaptation goals, it will verify the options that are available to adapt the system, and then pick the best one and adapt the system. Now, active forms also allows you to do online updates. Actually, by using these models at runtime, you can relatively easily update the logic, the feedback loop logic. So whenever you have changes where you say, okay, I want to change certain modules, or I want to add new adaptation goals, then you can, on the fly, update the models and continue the adaptation with your new models. Here you see a sketch of the runtime architecture. So the feedback loop that I showed you before here consists of feedback loop models. This is actually a network of stochastic timed automata in our case. And these models, they are executed by a model execution engine that can execute these type of models. And we use a statistical model checker to perform the runtime analysis. Here you can see an example of how at runtime that system is taking action. On the left-hand side, you see an overview of all the different configurations or a selection of configurations that system can have at that moment. And the dot here, the blue dot, is the one that is currently deployed. And as you can see, if the packet loss threshold is 10%, it is violating that goal. So then the system needs to search for a new configuration. So it will analyze, using statistical model checking, a set of configurations, and then it will select those that complied with the goal, all the green dots here. and it will pick the one that is best at that moment, the red star here. So it will reconfigure the system from the blue configuration to the red one. So to conclude, and this active FROMS is an end-to-end approach for engineering trustworthy self-adaptive systems. This feedback loop in our case is a model of a formally founded model. We use statistical model checking to make efficient decisions, and this feedback loop model can be updated on the fly if that would be needed. Thank you very much.
Let's thank the speaker. We have time for some questions. I will start. You present an approach that also comes with different steps and so on. How can an engineer of a self-adaptive system like IoT system that you use for validating your work can use this approach in practice?
Yeah, I have to say that this approach is not, it is a bit like, let me say, it requires you as an engineer to be familiar with certain technologies. So if you need to engineer a feedback loop model, you need to understand what are stochastic timed automata. And that, of course, might require you to learn something about how to model. Now, we have not by incident used these kind of models because they are actually, and we have worked with them many times, including with IoT companies. And these are pretty natural models. They are basically kind of advanced type of state charge that allows you to represent things pretty well. Also, these templates help you to design your own solutions. But I agree, it's a learning curve to apply them in practice.
Just a follow-up question. When you work with the IoT company and for the development of these models, were the engineers knowledgeable about them, or did you have to do some specific training or help them to develop this? Yeah, we actually worked together with them. So when the models were designed, to be honest, we did most of the design with their input. Yeah, okay, it was like, it is a learning curve, I have to say, yeah. Okay, we have time for more questions. Zeli? If not, I have another question still about this approach. You said that you have been working on this for several years with your team. What's next? In fact, next what we would like to do is this evolution step that you saw is currently manually. So actually it's the humans that do the whole evolution step. They redesign the models, they do the testing before they deploy it, they drive in fact the whole evolution. What we are looking into now is automating that step, which brings a lot of new types of challenges. And in fact, it is a kind of closing the loop of evolution, as today still it is a human-driven thing. We would like to make it a machine-driven thing. Okay. Let's thank the speaker again. Thank you. Thank you very much.